So hello everyone, welcome back to our Toronto AI in Robotics L seminar. Today we're glad to have Mathias Gehrig to give a talk on event cameras and how to make them useful. Matthias is a final year Ph.D. student at the Robotics and Perception Lab at the University of Zurich in Switzerland. Previously, he studied robotics, systems, and control after finishing his bachelor's degree in mechanical engineering at ETH Zurich. He also worked for 1 year as a research engineer at the Autonomous Systems Lab with Roland Siegwart before starting his Ph.D. His research is broadly concerned with motion estimation from event cameras and finding new ways to combine event-based and frame-based paradigms. Besides his research on event cameras, Matthias has also participated in autonomous drone racing competitions, while the team won the IROS 2018 racing event and achieved second place at the Alpha Pilot Challenge in 2019. So Matthias, we are all looking forward to your talk. The stage is yours.
Thank you very much for the introduction. Can you see the slides?
Yes, it's good.
Okay, perfect. Yeah, so today I'm going to talk mostly about event cameras and how I think we can make them useful. And it's quite an applied talk, I would say. So a few videos to show you what that means. And in the end, I'm also going to talk about different future works that we can consider. And so here in this first video, you can see the output of an event camera. When you look closely, you may realize that this person is actually a dancer. And what you have just seen is a space-time visualization of events. I will play it again. So here again, you can see the space-time visualization of events, and you can see that you get that kind of this continuous information flow in time. And this is probably a visualization that really shows the unique capabilities of event camera in a few seconds. Now, to be more concrete, so if you have a standard camera output, like a video, and you have this rotating disc, you will get fixed rate of frames, while the event camera here, shown as DVS output, gives you continuous streams of events over time. If you don't move the dot, then you have no events, while you still trigger frames of conventional cameras. And if you move the dot really fast, you get typically motion blur for video cameras during the exposure, but event cameras are very robust to this motion blur and can still, you can get still a good signal from this fast rotating dot. And yeah, so if you have a static camera, you don't see anything basically, but if you move the camera, you can see kind of the edges in the scenes. To be more concrete again, so if you have a video camera, the output of this video camera is typically fixed time intervals. So you have every delta t, you have a frame that your camera acquires. While for the event camera, it's a bit different. The event camera gives you events asynchronously, and you can see this on the bottom here. Between some 0 and delta t time, you get multiple events, and they are typically not synchronous and not fixed in a fixed interval. If we now consider a single pixel, so x, y, for example, the events are generated whenever the intensity change, so the logarithmic intensity change over time reaches a certain threshold. Here, I'm showing it with a sensitivity contrast threshold of C. So here I have a concrete example. Let's look at this continuous signal of intensity over time. The first event that is triggered is an on event, so its polarity is positive. And then you have 3 subsequent events which are negative because the threshold has been reached, the negative threshold has been reached 3 times. And again, if the intensity signal increases, you get positive events and negative events and so on and so forth. So right now, I think it's a good time to ask a question if this is clear or not, or if I can specify it in more detail. Okay, so I believe it's more or less clear. So the point is that we have every single pixel is kind of independent of each other, and we don't acquire frames anymore, but it really like per pixel event data. And yeah, now we come to the part where, yeah, what is the point? Like, why do we need event camera, or why should we care? So the working principle of event camera is quite different from a video camera, because events are triggered asynchronously, while video camera gives you fixed frame rate in a synchronous manner. And one important difference is that the update rate of an event camera is extremely high. So typically more than 10,000 kilohertz, so 10,000 hertz, up to 100,000 hertz. It depends on the conditions. While video camera, typically, if you don't have a high-speed camera that is designed specifically for this, you get less than 1,000 hertz. So on your phones, you typically have less than 1,000 hertz. The crucial difference is also that the event camera has an absolute intensity, that the absolute intensity cannot be observed by the event camera, while the video camera can observe this. And this is because of this principle that I just introduced one slide ago, where we only capture events when there is significant change. And because we only care about change in event cameras, we cannot capture this absolute intensity. So there is also kind of secondary effects that I personally consider secondary effects. They're not the primary effects, but they're also very interesting. For example, an event camera has a very, very high dynamic range, up to 120 decibel, while video camera, typically global shutters have around 60 to 70 decibel. To be fair, there's also now automotive cameras, which have also in the range of 120 decibels, global shutter, rolling shutter cameras. Then motion blur is also an interesting topic, because the event camera, due to its working principle, doesn't have an exposure time. So it doesn't really have the motion blur that you would expect from a standard camera. It still has some effects. So when you're in a more dark environment, you kind of have trailing events that are like a result of how these event cameras work, but they're typically very robust to these effects. And also due to the working principle, like static scene, if you have a static scene, we don't really observe anything typically, while the video camera, of course, can. And in the end, there is a kind of a trade-off that we make here. So for the video camera that you are all know very well, you have a trade-off between update rate and bandwidth. So you cannot have 1,000 or more hertz frame rate, because simply there's a limit on the bandwidth and probably also power consumption. So when you have your phone and you want to capture high-speed video, typically it's done on lower resolution and not 4K. For the event camera, there is a different trade-off. So the bandwidth is not really a problem. It's more about that you sacrifice the absolute intensity and instead get a high update rate for free. And to sum it up, these two cameras or these two paradigms are actually complementary. So you can see this here, where a person is moving the umbrella, like rotating the umbrella, but the background is more or less fixed. And you can see events are generated where the umbrella is rotating and the rest is kind of not triggering any events, while you have these fixed frames that give you additional information over only the event data. Well, now in this talk, I'm gonna build it based on this ML research lifecycle, I call it. So in an ML research lifecycle, of course, extremely simplified, we have a problem setting that we look at. For example, okay, which problem do we want to solve? We have a data collection phase, data preparation phase, where you have to acquire the data and prepare it. And then we have a model development phase, and where we experiment with different models. And finally, of course, model validation phase. And then we go back and iterate maybe on this. And in the industry, you typically also have model deployment, which we don't usually have in research. And in the first part of this talk, I'm going to focus on data collection and preparation. In the second part, more on models, model development and applications. In the third part, I'm going back and closing the circle with some open problems and what I think is interesting for future work. So first, I'm gonna start with addressing this data scarcity problem. So what do I mean with this? So, you know, in image-based and frame-based world, or in, let's say, in conventional computer vision, we have the whole internet. The whole internet is full of extremely rich data that we can scrap and build huge data sets out of. This is not true for event data, right? Event data doesn't really exist to such a degree. It's not commercially used. So we have to acquire this data ourselves. And this is a big problem for machine learning, of course, because yeah, we have to do it ourselves. It takes time. And so we did. So some 2-3 years ago, we started this project where we collected a large data set. And I'm quickly going to tell you about this because I think it's interesting. And we also build a lot of future work on this data set. And it's called TSEC. It's a stereo event camera data set, which is especially designed for driving scenarios. You may realize it looks like kind of similar to Kitty if you're familiar with that. So we have basically 2 stereo event cameras and 2 global shutter cameras at fixed frame rate, a LiDAR, and we basically acquire this data also with a GPS module and synchronize everything accurately and also calibrate everything accurately, which is very important, as I will show you later. So the question is, why do we actually need a data set? Are there not existing data sets already? And the point is, yes, there are previous data sets, but many of them have, you know, some issue that we would like to solve. For example, if you look at stereo, the problem of stereo estimation, an important part is that we need a sufficient baseline between the stereo cameras. And there is almost no data set previously with where we have sufficient baseline. For example, there's the MVSEC dataset, which is also a famous dataset in event-based vision, but the baseline is really small, only 10 centimeters, and the resolution of the camera is also small, so it's not sufficient for stereo matching. Yeah, so basically what we also have is color stereo global shutter. So stereo global shutter is kind of also important because it gives you complementary signal. And we also have this at sufficient baseline available. And we also have higher resolution than previous data sets, so 3 times higher than, for example, MVSEC. And the most important part is that we make really sure that the calibration and the time synchronization is done well. And this is what it looks like. So we drive around in Switzerland. Hopefully you can see this and it's not too stuttery. So on the top left, you can see event camera output from the left and right camera. On the bottom, the global shutter output, and on the right, you can see the LiDAR. And here you can see, for example, so an eye dynamic terrain scenario when you leave the tunnel. Yeah, so this is kind of the data that we acquired over time. And we did this in Switzerland, driving around for maybe, yeah, actually we drove around for more than 1 hour, but the final data that we upload is 1 hour of data, more or less. In total, we spent actually 2 years on this. So to build everything from scratch to data acquisition, data processing, doing everything, it really was really a lot of work. It took about 2 years. And in the end, what we also have is ground truth for disparity, optical flow. In the meantime, we also have some pseudo ground truth semantic segmentation, and we're also working on object detection ground truth. That's not there yet. So, and as I mentioned earlier, accurate calibration is very important because of 2 things, right? One of them is if you want to do research in multimodal input, then we have to be able to associate event camera and video camera. And here I show an example on our data set where we really, due to our calibration, we are basically able to map the events into the frame-based camera at pixel, more or less pixel accuracy. You can see on the bottom left, for example, there's a slight offset. This is because this mapping is relatively naive. You just assume infinite depth. So if you go closer, it's not actually 100% accurate anymore. Yeah. Well, so far to the data set. Now, I want to show you that we also trained a neural network for stereo prediction. So we want to see if our data is actually good. So we train neural network on the event camera data only, and we predict it to, but the model has to predict the disparity or the inverse depth essentially. And it does that really well on our data set, which gives us, hope that we had made a good job with calibrating the event camera together with the LiDAR. Now the question is, of course, maybe you ask yourself, okay, why did you record event cameras? Why did you put so much effort into this? I want to show you this video where there's a person running onto the street, basically. Like this car, this person is driving, a person is driving, and this person is running onto the street. And the person, there is an accident because the driver was not able to stop in time. And if you had, an algorithm that would be able to detect that this person is running onto the street in very few milliseconds, you could actually stop in time, or at least ameliorate the, the damages to the person. And the reason why event cameras could be interesting in this scenario is that if you look at simulation, you can see, for example, the same scenario, a person running onto the street, and the driver is not stopping. If you look at optical flow alone, you can actually see that this person, like this kid, is visible in the optical flow. So we could actually, have an algorithm that, for example, uses the events, computes optical flow, or implicitly detects a person based on motion. And this is one of the main motivations why we did this data set. And now if you look at optical flow in practice, so this is on the MVSEC data set. This is an older data set that is quite famous. We predict, so what I did basically is create a model, a simple machine learning model, and run it on MVSEC to predict optical flow based on the ground truth that this data set provides. And the output is relatively blurry, as you can see on the top. It's I was not really satisfied by this because this is far from what I would expect, from a machine learning model that is designed to predict optical flow. And the question is really why is this the case? And the reason is that the MVSEC dataset has some issues with the calibration, so it's not very accurate in calibration, and the temporal synchronization is also not 100% accurate. So just these slight small differences make a big difference in the end, and I will show you later why and what I mean with big difference. But first, we go to part 2, so applications of event-based vision. And now I'm basically looking at the problem of optical flow. What do we need to improve optical flow estimation with event cameras? My hypothesis was that we need better data, as I suggested earlier already. And we also need better methods. And in the next step, I'm basically addressing both problems. And for that, we were working on an extension of DSEC where we actually simply went through the data set and extracted static scenes. Because if you have a static scene, it's relatively simple to extract optical flow, although it's not perfect. For example, moving objects, you don't have the ground truth, but at least for static scenes, you have it. And then we create a relatively small data set of around 10,000 frames for ground truth. A ground truth frame looks like that on the right that I showed. And then we were experimenting with a better method, and we took inspiration from Raft, and Raft is kind of a neural network that is designed especially for optical flow for frame-based vision. But still, we were curious to see how can we adapt it to event-based vision and if it works well. And how we did that, and it's quite simple. So what we do, we have some duration of events that we consider. For example, here ti-1 to ti. During this duration, we create a dense event representations. It can be a voxel grid, for example, where we just interpolate events into a dense voxel grid, and that represents space and time, so time, height, and width. And we do this for two subsequent time durations or time windows. Then we extract dense features from these representations. One of them is a context feature. This context feature, the idea there is that given some context, for example, you see the ground in front of you, and you know that you are driving, that most of the data set is a driving car, then you can already have a good prior about what your optical flow should look like. But also, we can directly extract flow information from events without even doing some fancy cost volume extraction. But we also have a cost volume, and we use this cost volume to do iterative refinement of the optical flow. Just to give you a hint, so basically we developed this, we adapted a RAF for events. And on the MVSEC dataset, we improved the results already quite a bit against previous methods, for example, EVFlowNet. But on our dataset, which is substantially more challenging, we can reduce the endpoint error by a factor of almost 3, which is quite remarkable, in my opinion. And well, how does it look like? Let's see. So these are the predictions from our model on the top left. And you can see that you can basically see the structure from motion, essentially, that you get from the events. And the reason for this is that, mostly the data is just substantially better in terms of when you do supervised learning. And here we drive through a tunnel, and here you can see this HDR scene where the raft baseline struggles a bit because of the overexposure in the global shutter frames. Yeah, the take-home message from this project was, while ERAFT, the method itself, is surely better than the previous method, the data was the most important factor. So just as paying attention to calibration and time synchronization really paid off, I would say. In the next project that I'm presenting here a bit in more depth is about dense pixel tracking from events and frames. And I'm basically asking the question, how can we better leverage the high temporal resolution of the event camera? We partially did it already in the previous project, but it was not very explicit. And now I wanted to push it to the limit. And the idea is essentially that we have, for example, 2 frames available, so the first and the second frame, and the events in between these 2 frames. And we want to predict the continuous motion of pixels in image space. And the general idea is that we have event features that we extract from the event stream. So these are fixed number of features, in this case n. And we have features that we extract from the 2 frames, so the reference and target frame. And finally we predict the optical flow from the reference timestamp onwards in time. Because in optical flow, you always have to choose a reference frame or a reference timestamp. And the idea is that we can represent the tracks of features as Bezier curves. So in the end, what we predict is per pixel, a Bezier curve that maps time to the displacement in continuous time. And the model needs to estimate for every pixel P1 to Pn. So it needs to predict the Bezier curve components, or the control points as they are called. And how this is done, this maybe looks a bit overwhelming, but I'm going through it one by one. The idea is that we have, again, these iterative refinement steps that I propose. And we start basically with a Bezier trajectory representation. So we have these basic control points that we predict. We also have several features that we extracted from the events in time. And we also have some context encoding that we can use to improve the performance. And then what we do is we look up, given the Bezier curves that we have, so basically given the continuous motion of the pixels in space, we go up, we go to the different timestamps of these correlation volumes that we compute and extract locally the features from these correlation volumes. So this is similar what is done in RAFT, but we basically generalize it to multiple correlation volumes in time. And our model predicts the Bezier curve starting from 0. So we say, okay, no pixel moves. And then the model predicts always this delta pi. So it iteratively adds a refinement to the existing Bezier curves. Any questions so far? Is this more or less clear?
So the correct correlation works so great is still some from some small time window of events, right? And doing some correlation between the two features from two event time windows, and so that you can get a.
Exactly, yes. You can think of it like this, yes. So basically we have these different time windows that we look at, and we shift this, how it's done in the implementation is basically we have these time windows and we shift them slightly and extract the features again. So we have kind of a sliding window that we have, and we place it at several different timestamps to extract the features. Yeah, and this is basically already the core idea. And I would say, yeah, it works decently well. So I'm showing you a real world example. So this was training simulation. I'm going through that as well, but we deployed in the real world. And oh, now the video is stuck. Sorry. Okay. Yeah, now you can see, for example, there is this person trying to hit the ball, and we basically predict per pixel, just showing a few pixels, the trajectories that are predicted. And this is the umbrella scene where we predict that it's essentially rotating. Yeah, and how we trained this model, we created a synthetic data set. It's inspired by the data set that Flying Chairs, it's called actually, Flying Chairs data set. But what we have here is a bit different. We have, instead of a fixed displacement, we have a continuous motion of the different objects. So we place randomly some objects in the scene, and we apply continuously some similarity transform to these objects. And then we have the ground truth flow in time, and we can use this to create a supervised learning problem. So in fact, what we do, we have this loss function. This loss function is simply the Bezier curves that we have per pixel are supposed to predict the displacements that we have at several different points in time for all the iterations and for all the pixels essentially. And yeah, this gives us the results that we can directly transfer to the real world, and which works quite well already. And some key observations that I found in this work is that images always improve the optical flow results. So this model also works only with events, so the images are optional. But if you add the image data or you extract additionally features from frames, you consistently improve the results, not only in simulation, but also in the real world. And you may ask yourself, okay, but I thought maybe optical flow is like great for event cameras. Do we really need frames? And the point is that event cameras, they have this threshold, like this threshold that I mentioned in the beginning, this contrast sensitivity threshold. And what this does is it basically quantizes the contrast. And this quantization of the contrast makes you lose a little bit of detail in the scene. And these details are sometimes important, for example, to match the trajectory from the reference time to your target time. This is where the frames can really help. And I also did several ablation studies here. And one of them is, I think it's relatively obvious, but it's that intermediate correlation lookup helps to improve the results. So this basically validates that it makes sense to have these multiple feature extractions in time and to build these correlation volumes. But what surprised me the most is that simply predicting Bezier curves helps a lot. So if you just predict basically the displacement from your reference time to your target time for optical flow, this is much worse than predicting the Bezier curves. And yeah, how we can think about this is that if your model has to predict a continuous trajectory in time, and you give it the freedom to actually, to predict a continuous trajectory, then this somehow facilitates the learning of or the problem sufficiently to solve it. I found this quite interesting, actually. Okay, so next I'm gonna go to some applications of this idea. So here you can see that what we worked on is, for example, frame interpolation. And frame interpolation is a task where you have low frame rate input and you want to predict the intermediate frames. And in this work, what we did, it was a collaboration with a company, is that we use events and frames to predict high temporal resolution video. And you can see this is quite an extreme case where you have complex motion that you have to predict at 20 times, almost 20 times higher frame rate, which is a very, very difficult problem. And also, yeah, for example, if you have these transparent fluids, this is very challenging for video frame interpolation. Okay, and the key idea in this work is kind of similar to what I presented you before. So what we do, instead of just linear optical flow or linear prediction in time, we do a continuous prediction of the motion in space and time. And with this, we can essentially predict where each pixel is moving over time to synthesize intermediate frames. And yeah, I mean, this is kind of the key insight. Of course, there are multiple other things that need to be done to make this work, but I would say this is one of the key components of this method. And the results are quite good. So you can see here to the left, the input frames and the input events, and on the right, the predictions from this data. Another case where you have some very dynamic motion, very complex nonlinear motion, and also transparency. And typical problem, yeah, fire is also very challenging to interpolate, but it can be done successfully with this combination. And this goes a bit also hand in hand with the previous point that I made, that these modalities are complementary. Okay, so what I have not shown so far is, to keep it a bit shorter, is our recent work on sparse graph neural network-based object detection. And the point what I'm making here is basically I'm going to just over some things that we have also done recently, but I've not shown, because I want to highlight that, this research discipline is very interdisciplinary and there are many different things that can be done. And also, for example, recent work on dense transformer-based object detection. It should be coming out soon, that we have also done. And other work on data-driven key point tracking. So here the task is to track points in space and time, given, for example, a single frame. And this typically has been done with model-based methods where we model the event generation model, or we use the event generation model to predict these trajectories. For the first time, we also found a way to do this in an event-driven fashion. So finally, I also want to come back to open problems and research direction. So I've spent quite some time now, I would say, yeah, basically 5 years almost with event cameras. And I also want to highlight some things that I found, and maybe that would be interesting for future PhD students to work on. But first, the conclusions in this talk is that I think really high quality data has been a key component in our work. So I think it cannot be underestimated. And it's also a very important part of research in event-based vision, because we, as I said, we cannot simply scrap the internet and collect huge amounts of data that are of high quality. So we have to do it mostly ourselves. And this is also whenever you change the application. So let's say you want to have a different problem that you solve. Often you have to really go back to the basics. So you could work maybe with some given data set, but maybe it's not good enough. You know, your method will mostly be constrained by data. So you might have to really work on the data collection part first. Event cameras are excellent for optical flow estimation. I think I hope this more or less I could convince you about this with ERAFT and the pixel tracking method in continuous time. And also our works on frame interpolation, where we show that optical flow and event cameras can really help to improve the results or get really excellent results. And in my work, I've also found that frames are complementary to events, and they essentially always help. So I would say almost regardless of the problem that you have, frames typically help. And this is because of their complementary nature. Now I also want to highlight a few open research topics, and a disclaimer, this is biased, of course, because it's my view, but I think there are many more points that I'm not covering, and everyone should be very open to this. But I still want to say a few things about this. And the questions that typically we have to ask ourselves is, what are good problems to solve with event cameras? This, I think, is one of the fundamental questions, because we are in this position where we have to justify ourselves. Because why would we use them, right? It's a good question. And is there room for improving the existing methodologies? I think this is also an important question, because we should not have we should not believe that the methodologies that exist for now are the only ones that exist, and they are potentially already maxed out, or there's no way to improve them. And essentially, first, I'm going to quickly talk about under or unexplored applications that come to my mind, and also some open question methodology that I personally would consider. So first, in application, I think tracking is quite underexplored with event cameras. So of course, there are several works. For example, in human pose estimation, there is at least 2 or 3 data sets now. But simply, I think, if you compare the data that we have to data that people use in computer vision otherwise, it's a big difference. I cannot overstate that. So if we have, for example, a great, if you think human pose estimation, interesting problem, there is a huge, I would say, a huge opportunity there. And the same for maybe some more AR and VR application, for example, hand pose estimation or tracking. I think it's also quite unexplored. Key point tracking is also something that multiple people have worked on, but I still think we can improve on that. We have also worked in this direction. Maybe you're inspired by that in the future. And in general, object tracking is almost unexplored in a way that I think there's still many open questions. And even detection itself. So moving object detection is something that also is quite a topic that people have explored in event-based vision, but I still think it's very far from solved and very far from away from what we could actually achieve. The question is, of course, always in moving object detection, do we need optical flow? Or do we need something even more general than optical flow? But I think optical flow is probably quite a good starting point. But it needs to be very fast. So in event-based vision, there's typically this paradigm. Either you have kind of an offline processing approach, like in frame interpolation, where you don't really care so much about high speed. I mean, it's also important that it doesn't take minutes, but it's not real time necessarily. And the more real-time applications where you have causal inference, where you really need low latency. And I think optical flow is interesting for event cameras also because I think we can do without too much or very expensive computation. I've shown you eRaft, which works very well, but it's not, I would not say it's optimal trade-off between performance and inference time. So there can be a lot of improvement there. And yeah, this should be probably combined with reliable ego motion estimation in the loop, because typically if you want to extract moving objects, you need to know how is the camera moving with respect to the scene. And I don't think this is solved either. And in the end, like, for example, low latency object detection is also an open problem. How can we detect, or how can we use events to better detect objects at very, very low latency to, for example, stop accidents or stop the car in time? And then finally, what is also almost, yeah, I would say very open is closed loop control. So closed loop, like vision in the loop, essentially, where you have an agent that takes as input your measurements, such as events from a hybrid camera, some other measurements like IMU data, or and you basically give commands to the robot to behave in the way that you define it, goal-oriented behavior. For drones, this could also be done for cars or race cars or whatever application comes to your mind. I think for events, it's just important that the motion should be substantial for this kind of problem. Otherwise, event camera doesn't give you that much benefit. Yeah, I would say. I guess, again, this is my personal feeling. Then coming to the method. So if you have any questions or comments, let me know, right? I'm just giving some, I would say, biased insights. Well, now coming to the methodology, I think there's also many open questions in how we approach, how we develop our methods. And this is also biased towards machine learning application, deep learning. And in there, you have the problem of efficient and effective, oh, I made a mistake, low-level processing of event data. So there are different ways of processing event data. Typically in neuromorphic engineering, this is done with spiking neural networks. So spiking neural networks are biologically inspired neural networks that are extremely sparse. But they are not very often used in conventional deep learning. Conventional deep learning is more about CNN, RNN, and this kind of dense methods. But you can even use conventional deep learning methods like GNN to create like sparse processing pipelines. And I think the question is still open, like how to do this best, or what are the best trade-offs there. And we have works covering all of these aspects as well. And maybe you can also combine it, of course. And the question is also high-level processing. So how do we effectively extract spatial temporal features from event data? And this is open question still, probably in single modality. So if you only have events, so not considering frames at all. So how can this be done efficiently? I think it's still open. And also, how do we do multiple, or how do we combine multiple modalities? I think this is maybe more close to being solved now, but it's still a very interesting question. And then in the end, one thing that is almost completely unexplored is pre-training and self-supervised learning, as an example. So when we have machine learning models that we train on event data, we typically train from scratch. But this is very different from people who work on conventional frame-based vision. They take a pre-trained checkpoint from ImageNet, or they have self-supervised techniques. They can train it on video data or image data, and this really reduces your development time and improves your results. But we don't have such things yet in event-based vision, and this is also this is kind of also an open question in my opinion. So finally, I hinted this in the abstract of the talk. What do we need for widespread adoption of event cameras? So this is, of course, a very difficult question to answer, and I'm only, again, giving my biased opinions, which may or may not be true. So one point is application. So we need to find a high impact, we need to find an application where event-based component has really high impact. I think, for example, optical flow is a low-level vision task, which really benefits a lot from the event-based components. And also, for example, the tracking problem is very attractive for event-based vision. But maybe there are more, right? I don't know all of them, and I'm also constrained in my view. What is also extremely important is high quality data for this application. I've mentioned this before. And then also the combination of model plus hardware. What do I mean with this? So event-based vision is not actually very well suited for, or asynchronous processing is not very well suited for GPUs, for example. So we can design methods that run very fast on GPUs, but potentially we also have to think in the future about ways that, if we should use kind of different hardware that is better suited for processing event data. I think this is also kind of an open question. So there's, of course, neuromorphic hardware, which is designed for spiking neural networks approaches. There's also graph-based accelerators like the IPU from GraphCore, which we also haven't used so far. It might be interesting to work with. In the end, what is very important to really break through the ice is to have a high quality, a sensor with high quality events and frames combined. Because basically all of the research that we've done, we have shown that this combination helps, but we don't have a sensor that combines both in a very elegant way. Because there are these Davis sensors that have frames and events, but the frame quality is really low. So it's not really, it's really holding back the, it's holding back the performance of our application if you use such sensors with low quality frames. And finally, what is also needed is, in my opinion, a community that's very open-minded. What I mean with that is that we don't basically exclude ideas from each other. We say we have opinions about this is the only way how we do this. Like we can only use sparse or dense method to do this because this makes most sense. I think in the end, we only make progress if we are open-minded and allow different applications to be explored and different methodologies to be explored. And I think I've already come to the end. I thank you very much for listening, and I'm open to your questions. Thank you.
Thank you, Matthias. Thanks for the great talk. So now it's the QA time. And first, there's a question from the audience in the chat. So it's from Ben Isaac. Thank you for your presentation. I was wondering if you have come across applications of event-based cameras in fluid dynamics and aerodynamics research for like tracking the motion of fluid or particles in air. So some of the existing methods are particle image velocimetry and laser Doppler velocimetry. And are there similar methods in event visions?
Yeah, that's an excellent question. So I think there is 1 or 2 papers that are going this direction that try to track basically fluid particles. There are 2 works. I don't remember the title of them. I'm not sure if I would consider the problem solved though, but I think it's an extremely interesting application. So what we have done, we also collaborate. We went once to EPFL and we collected some data with the fluid dynamics group there, and the results look really amazing. So I think it's really possible to extract the motion in fluid dynamics with event cameras, and I think it's still kind of an open question how to do this best, though.
Oh. Is there a paper or like?
Yeah, there is. Or... No, from our side, not. But there is other groups that have worked on it. I think 1 or 2 papers should be out there. But to be honest, I could not tell you the paper title right now. But it's super interesting direction to explore, of course. Yeah.
Thank you. Yeah, and if others have questions, please just unmute yourself and ask Matthias. So I have a question. So like, how is the generalization of models trained on one event data set? Like if you train a model on the what's that called? The DVC or the the autonomous driving data set you just mentioned in your first in the eRAFT project. Can you also generalize to the MVSEC data set? Or can you generalize to some, I don't know, like indoor event data sets?
Good question. So one, I have to mention something quickly. I'm not sure how long my battery will last. It might randomly drop off. I think there are two options. Either I get the power, which takes 2 or 3 minutes, or I might randomly drop out at some point. What is your preference?
I think you can get a power.
Okay. We'll take one and they'll be back soon.
Yeah,
Sorry.
sure.
Right, so I'm back. You hear me?
Awesome. Yeah.
Okay, great. So the
Oh, wait. Sorry. I think I cannot hear you.
Can you hear me now?
Yes, works.
Okay. Okay, so the question was about generalizability, I think, right? From DSEC to MESEC,
Yeah.
for example. I think we haven't tried that, but I would expect it to work from DSEC to MESEC. But you might have to, I'm not sure if it's, let's say if it's required to rescale the input. So it could be, for example, that it works better if we rescale the input of MESEC to the resolution where it was trained on DSEC, but I'm pretty sure it should work well. But from MESEC to DSEC, I'm not so sure about that. I don't think it will work because simply the output is not very good. But I haven't tried it, like this cross data set validation.
But like, is it because they are captured with the same event camera, the same type of event camera, or not?
Yeah, this is a different event camera. On the MESEC dataset, you have Davis 346, and the DSEC dataset has a Prophecy dataset which has higher resolution. So you have like 3 times more pixels, basically.
But there are like contrast threshold is the same.
Yeah, though it's different. I mean, the contrast threshold is something that it's more like a theoretical concept, but in actuality, like the contrast threshold is not something that is very easily to estimate because it might be different for each pixel, for different cameras. it might vary depending on your environment, how the intensity and so on and so forth. So once very early on my PhD, I was like, okay, now I'm going to estimate the contrast sensitivity, and it doesn't really work that well. So, but I don't think that this is necessarily a problem, because DSEC, the DSEC dataset has many different environmental conditions. So we have very dark scenes, we have very bright scenes, we have high dynamic range scenes, and we have flickering of street lights. So the contrast threshold, I don't think that it will make a big difference if you change the data set, because we have such a variety.
I see. So basically, if you have like two data sets captured with two different event cameras, as long as you kind of rescale the image size or the event size, then we can expect the model to transfer, right, to generalize.
Yeah. Well, I mean, what is more important is kind of the motion of your camera. For example, if you take ERAFT as it is pre-trained and you deploy it on some indoor scenes and you have handheld motion, I'm not sure it will work super well, because the model was just recorded on driving scenes, right? So there's a huge prior on what it expects to see. So there, if you want to generalize to different scenes, you also need more variation in the data set.
Yeah, that makes sense. Okay, any other questions from the audience?
Yeah, I have a question. Yeah, the frame interpolation results using like image-based camera is really amazing. I'm just wondering, have you compared that with some other like interpolation network based on purely RGB image?
Yeah.
RGB video.
Yeah. So there are multiple comparisons that we have done in the paper. So the initial one, so there are basically two papers. There's timelines and there's like a follow-up version from that. I was only participating in the first version, and there we compared against state-of-the-art on data sets that they compare on. But there, the tricky thing is that we could mostly compare against their method on their data sets. So sometimes you had to kind of synthesize the events between frames for some data sets. But yes, we compared against the state-of-the-art method there as well. But I mean, the most recent one, I don't know, like how they compare. Like there are, of course, many works in between when we did that and now.
And like, how does pure RGB method work?
I can show you maybe quickly. Let me open.
That'd be great.
So your question is how a pure RGB method works.
Yeah.
Okay,
compared to like your work.
Like performance-wise, you mean?
Yes, performance-wise.
Okay. Let's see. I'm opening the data. Okay. So I'm going to share a screen again. Share. Can you see this?
Yep.
Okay. Yeah, for example, this is from the paper that I just said, timelines. And we can see, for example, that we compare against on Dane super slow-mo, PMBC, and EDI. So I would say some well-known competitors. And the difference in PSNR here is like 3, around 2.5 for Dane, and super slow-mo it's over 3. And there we have also recorded our own data sets. Sorry, going here. This data set is called HSERGB, and what we did here to have a better, more fair comparison is we have a beam splitter set up where we have frames and events aligned on the same view of the camera. And here you can see, for example, there's a bigger difference. So Dane to timelines is about 5 PSNR, and super slow-mo even more. So I think there's quite a big difference compared to what was considered state of the art at that time.
What is the size of this the data set you collect? Like how many videos? The super resolution. Sorry, the video interpolation. Just curious.
How many sequences?
Videos. Yeah, sequences.
Yeah. That's a good question. I think it must be around. So for that part, I think it's not. I think only a part of it is publicly available because it was done with some collaboration with a company. But I remember it must be at least like 20 to 30. But it's, yeah, I think it's not a lot, but it's around that, I would say. Around,
so that's
probably 30.
Already like enough to train a neural network? Because I kind of feel like
yeah, good question. No, it was pre-trained, so I think it was also pre-trained on a synthetic data set where I think this, if I remember, is this GoPro data set, for example, where it's usually trained with that. So the frame-based methods trained with the GoPro data set. What we did, we use a trick that I haven't shown you here from a work that we did some years ago, where we use a frame interpolation method to generate synthetic intermediate frames. And with the synthetic intermediate frames, we create events. And then we have the synthetic events and we have the real frames. And then we can pre-train a model based on this, on existing data sets, basically.
I see. Makes sense. Makes perfect sense. Okay, any other questions? Maybe the final call. Please just
I had like a short question. Thanks for the nice talk. So do you think your work is very much learning based? Do you think that there's some like open research questions in more, classic state estimation with event cameras? Like is this, I guess the reason you go directly to learning based is there's so much research, like so much progress recently to kind of exploit, and it makes sense to use learning because it works so well on like camera, like RGB data. But do you think like in RGB research, we started with classic and then went to learning? Do you think that we kind of skipped the classic part, or has that been done and just didn't work so well?
Yeah, there's a lot of work actually on like model-based, event-based vision. So using the generative model, there's a lot of work that I have not discussed. For example, even in optical flow estimation, there's this idea that you can, or like let's assume like feature tracking. There's one famous method from a other PhD student in our lab who basically used the generative event model to compute locally optical flow to create feature or key point tracking method. And this method is like super elegant mathematically, and it also works very well. And so, I mean, there's a lot of work in this direction already that I haven't discussed. But typically the problem is that if you have the simple model of the event camera is often not very accurate. And this is not, it's almost impossible to model, I would say. I mean, there are attempts to do this, but it's very difficult to use this model, this very complex model, then in a real world application. And yeah, that is one thing to consider. There's a lot of work already done. And the second one is that I just basically my personal belief that the model-based component is maybe better suited for geometric modeling. For example, in visual odometry or visual inertial odometry, the key point extraction phase is something that is still possible with model-based methods. I mean, Harris corner detection and so on and so forth. But for event-based vision, this is also already quite complicated actually to do, because you have the spatial and the temporal component, and you have a very complex event camera model that maybe you don't know. So in my opinion, this is why I basically focus very much on machine learning, is that basically feature extraction stage is just much simpler to do with a neural network than with you know, to do it yourself. And I believe more in the part where, for example, when we say with visual odometry problem, that we model the geometry on a higher level, basically, not on the low level part. Yeah.
Okay, that makes sense. Thank you.
But again, like, this is just my biased opinion. But you know, I don't have a strong opinion. Like, there are many cool works model based that also work well.
Good, thanks.